All right, we are ready to begin discussion on the sine and cosine functions. We've been working with sine and cosine in right triangles, but now we're going to go outside the box and think of them in a different way. So I want you to think about the functions we've been doing. We've been sticking with 30, 45, 60s, and the 90s because they're right on. And I've drawn a little unit circle there for you to use. But you should be able to now, without any hesitation, go through and figure out the exact values. This is not a calculator activity. This is an in your head. Go through and say, all right, she made me memorize those three combinations. And what were they? Well, sine of 30, sine of 45, sine of 60. So we did them in order on purpose. And then we traveled to the different quadrants. So for example, if we knew sine of 30, sine of 45, sine of 60, how that related back over to the angles that would have matched up with them in the second quadrant, in the third quadrant, and in the fourth quadrant. So you should be able to go through right now, and I'm going to give you a few seconds, to give me every single sine, cosine between 0 and 360 that you should know exactly by now. Again, no calculator. So I'll give you a second to do that. Okay, so now that you've gone and filled your little chart in and you're saying, well, you know, I did, but I didn't see the pattern. So that's what we definitely want to look at. We want to look at what some of the patterns are. But let's check and see what results, maybe what changes you have to make if you made some mistakes in your setup. So taking a look, this is our sine, cosine tangent combination. And remember, we said cosine is x, and that's why we have it listed first, and sine is y. So that's like our x and our y values. Theta is our unknown angles. And we went right down, if you remember. The sine of 30 degrees was 1/2. So here's our three right here that we were supposed to have memorized. And if we memorized those along with the 90s and multiples of 90s, which were easy because we were just spinning straight on the axes, then we should have all the rest of them memorized as well. So looking at yours, you should see some patterns. And I'll just point out a few as some of you are changing your tables. Notice that all the 90s, 180s, 270s, and 360s can only be 0, 1s, and negative 1s. They can't be anything smaller. They are at the edge. They are the extreme maximum value of our unit circle. However, the 30s and the 60s we learned were complements. So if I said the sine of 30 is 1/2, then I knew the cosine of 60, its complement, was also 1/2. So when you fill in the sine of 30, you immediately can go and do the cosine of its complement. So on all of these, sine of 45, same thing. Sine of 60 would be the cosine of 30. And so you can go and fill them in very quickly. And the only thing you had to keep track of on the farther you rotate it around is obviously, were we in the plus-plus combination? Were we in the minus-plus combination? Were we in the minus-minus? Or were we in the plus-minus combination? All those situations you had to take into account. And you'll notice there is a range. So, for example, x values. Where are x values negative? Well, from 90 all the way over to 270, if you look at your, and they are. All the way over to 270 is back to a 0, 1, or negative 1. And then they get positive again. Well, ask yourself, where are the sine values negative? Well, the sine value negatives are negative down in the third and the fourth quadrant. So where is that? From 180 on. So if you notice, the sine values are all negative from 180 on. So there's some patterns you should have seen, and we're expecting you. But now I want you to think of it as this way. We have our circle, and we've been in our unit circle. But I want you to come, and I want you to take a scissors, and I want you to cut it, that circle, which is one unique piece, and I want you to cut it right there. Think of it sort of like a lasso, and we have an end of it. And if we just sort of snap it out there, we should be able to get some different looking graphs. So if we take our sine and cosine graphs and place them on an XY linear looking graph, then we have a little different situation. So take a look. You should now be able to say, well, wait a minute, the domain the range. What are the x-intercepts? What are the y-intercepts? So talking about them real briefly. It looks like if we start looking at domain and range, x and y, so the eyeballs are going left to right, and on left to right on both of these, you're seeing the same kind of things. 0 to 360 is all I have in view here, but you could go negative. So it looks like we're going to infinity, positive and negative, as much as you want, all real numbers. We're evaluating any kind of angle, any size that you like. But the range, take a look, up and down. Both of these ranges are similar. We're seeing these wave-style graphs, but they both peak at a 1, and they both have a valley at a -1. So their highest point is 1, their lowest point is -1, so that would have to be our range. X-intercepts. If you start looking at x-intercepts, the x-intercepts on the sine versus the cosine wave. On the cosine, x-intercepts are right here. They are characterized differently than the y-intercepts. Again, the y-intercepts, there's the y-intercept for the cosine, there's the y-intercept for the sine. So start looking at those features and you should be able to come up with a list. And that list should look very similar to this. Domain, all real numbers for both the sine and the cosine wave. And the range, all real numbers from 1 to -1. The sine wave graph has y-intercepts of 0, has an x-intercept of the even multiples of 90. If you go back and look at the sine wave versus the cosine wave, and let's just do that again, even, so 0, 180, 360, that's 180 times 0, 180 times 1, 180 times multiples of 90, sorry. 90 times 0, 90 times 1, 90 times 2, 90 times 3, 90 times 4. So we got a 90 times 2 and a 90 times 4 here. We have a 90 times 1 and a 90 times 3 here. So the cosine is your odd and your sine is your even. And that's what we were talking about here. So the sine wave has the even multiples of 90 and the cosine wave has the odds. A couple other characteristics and things you need to look at that are new. If a graph can be mapped to itself under a horizontal translation, both the sine and the cosine are periodic. And you saw that they looked exactly the same in terms of their peaks and their valleys, the width of the curve. And so we can say that these two graphs are really congruent and that they have a horizontal translation of 90 degrees. And again, 90 degrees, if we go back to, it's going to be 90 degrees. If you take cosine and say, well, wait a minute, when am I going to get it? We would have to take the cosine and shift it 90 to the right to get it match up with the sine, and we'd have to take the sine and shift it 90 to the left to get it to match up with the cosine graph. So that's all we're saying when we say they can be translated, and when they are, they will be exactly alike. New word, that we can say that these are both sine wave graphs, even though they're slightly different, but they're also sinusoidal. All of you who like to play Word with Friends, Scrabble, etc., got a new word you can use there. All right, so knowing that, we should be able to discuss what a sine and cosine graph looks like. The only other thing is we need to draw one by hand, and also check and see if we can do it with the calculator, and we'll probably be doing that in class together.